by Professor Boxman, and about the development of pulse glow discharge.
Well, I want to acknowledge my colleagues at the University of Sydney, where this work was performed. And the background is that there's an interest for various kinds of biomedical devices to produce a surface which will be a host to organic molecules of various kinds. And a surface which can do this is amorphous carbon, and a way of producing it is by means of plasma-assisted chemical vapor deposition, or PACVD. And one way of performing the PACVD is to use a pulsed abnormal glow discharge. And these glow discharges are known for having various regions, the negative glow, Faraday dark space, positive calm, etc. But when this is done in a pulsed environment, the question is, how quickly do these various regions form? To study this, we used the following apparatus, of which only the bottom part is relevant. All of this apparatus is part of an effort to develop a graded coating, starting with vacuum arc deposition of a metal and changing to a carbide, and then ending with a amorphous carbon layer. But what's relevant for right now is just this electrode here, which serves as a cathode, and the surrounding chamber, which serves as the anode, and a pulsed bias supply, which is connected to the cathode by means of about 2.5 meters of coaxial cable. This cathode is 80 millimeters in diameter, and the anode is about 30 centimeters in diameter. To study the formation of the sheath, we used an argon gas at 97 millitorr, and the plasma was excited with 1.7 kilovolt pulses, 20 microsecond duration, at a pulse repetition rate of 100 hertz, and this was applied for 2.5 meters of coaxial cable. We measured the current and voltage waveforms at the power supply, in other words, before the cable. And we photographed the discharge using a conventional digital camera, and then a high-speed framing or stick camera that we operated in the framing mode by Hamamatsu. This camera would produce 8 frames with a framing interval of 1 microsecond and an exposure time of half a microsecond. And in order to get a strong enough image, 100 pulses were integrated, but each frame would look at the same segment of time. And then we used Hamamatsu software in order to obtain intensity profiles. Now, when we photographed a discharge using a conventional camera, which is basically integrating over many pulses and over the duration of the pulse, this is what we see. We see the very typical structure of the glow discharge. This is the cathode, and surrounding the cathode is the negative glow, which is the brightest part of the discharge. And then after that is the Faraday dark space, and then further away is the positive column. The question that arose, of course, is how quickly does this structure establish itself? On the left here is the sequence of photographs taken by the high-speed camera. These are organized as in the sequence 1, 2, 3, 4, 5, 6, 7, 8. And what we see is basically the same structure in all of the photographs except the first one, which we'll see actually occurred before the current had established. And then if we made a intensity profile over a swath of image space, starting from this point at the corner of the insulator and going through the electrode, what we obtained was the following. We can see the dark region in the center is basically the the electrode. Surrounding it is the negative glow, then the Faraday dark space, and then the beginning of the positive column. On some of the profiles, we see what looks to it, what appears to be, forgetting the word, striations in the intensity. What's interesting is that, albeit that each of these frames, if we go in the sequence from the first frame to the last frame, the intensity is increasing. The placement of these various features is approximately the same. We can see this more graphically in the following waveform. If we start from the bottom, the square waveform is basically the gate pulses going to the camera. So we can see the location of each frame in time. The location of the negative glow is shown here, the Faraday dark space here, and the positive column here. And basically we don't see that there's a lot of change in position. And during this period of time, there's some transient currents due to charging of the coaxial cable, but after this dies down, we see that the current is increasing. Despite the fact that the current is increasing during the duration of the pulse, the location of these features was basically the same. There was basically no significant change in the features during the first 8 microseconds of this discharge in terms of their location. Only in their brightness, but not in their location. So the conclusion is that the classical features of the glow discharge, the negative glow, the Faraday dark space, and the positive column, are all established within about the first microsecond. And the position of these features do not significantly change. I thank you for your attention, and I hope I made up a little bit for the time we took during the first session.
Thank you. Questions?
This is actually a very good demonstration of performance of electron kinetics, because the location is determined by energy relaxation from cathode to the. My question maybe is, why are you surprised, right? That's what we expect to be.
We're not in the least bit surprised. One of my co-authors, Annie Weeks, is in fact working on a model that basically has predicted exactly that. So there's no surprise, but it hadn't. Some of the features had been measured, but others had not been. So it was worthwhile to actually see that this was in fact happening.
And if you will decrease the pulse duration but put much more voltage or current, or you will increase the pressure, what will happen?
No idea.
Oh, yeah.
We'd have to run the model. Okay. Or do the experiment.
I see.
I mean, eventually, if the pulse is short enough, we should get into the regime where these features are still being built. But we're talking about more of the nanosecond regime, not the microsecond regime.
Mm-hmm. Other questions? Oh, okay. Thank you once more.